first I do a small pitch here for ECCV. So there is the conference, of course, and I hope many of you will maybe attend that. But also, there's for some of you, there might also be interest in attending the workshop on recent trends in computer vision, which essentially is after a program committee meeting where we have all very strong people in the field. They will actually we'll organize a workshop just after that with all of those people presenting their most recent work. And everybody is welcome to attend, and so reserve the date if you're interested. 16th of June, there will be about 30 talks from 30 different hour chairs. Okay? So, and actually there will be plenty of room. And worst case, we have reserved space in the bunkers of ETH for students to, to be housed if the hotels are all booked out. Okay, so what I wanted to talk about today is about 3D reconstruction from images, but at the same time to bring that together with recognition. So in the area of computer vision, there's two big problems. So one of them is, given a number of images, to extract geometric information from those images. Okay? So that means figuring out, if you have multiple images of the same scene, figuring out where the different images have been taken from. It means extracting the surfaces of the scene that you observe. And I will, in a moment, I will show a few examples and applications for this. So that's one area of computer vision which really tries to extract this information from images, typically from more than one image of a scene. It could be a sequence, you move through a scene. It could be a robot that navigates through a scene and needs to preferably not bump into too many obstacles. It can be a car also nowadays, or it can be that you want to survey a building and you want to reconstruct the geometry of the building. This is actually a very old field that predates by far computer vision. It's called photogrammetry, which is essentially extracting of these measurements from photographs. It's almost as old as photography, actually. If you look it up, it's more than 100 years old. And so it has been done right from the beginning of photography. People have used those photographs to make measurements from it. So that's one area of computer vision. Another area is recognition. And so there, the question is trying to develop algorithms which from images will try to figure out what you see in the scene. Okay, so you want to see, is this a building? Are there trees? You want to answer these more semantic questions and try to interpret what you see in the scene. And actually those two those are the two probably biggest areas in computer vision. There are a number of smaller areas, but mostly they align more with reconstruction or with recognition most of the time. So in a way, this really has been a big division in the field, with really people mostly being focused on solving one subproblem or being focused on solving the other subproblem. But not many people have tried to bridge the two. You could also say that there was a huge progress in reconstruction, in geometry, in the 90s. And then between 2000 and 2010 or so, there has been huge progress in the recognition area. But now also this progress is a bit saturating. And so now in the field, there's really a lot of people are starting to try to see how can we bring those things back together and maybe that way achieve further progress. Okay? So here's a picture of what we do. So we have a number of images that observe a scene. By correlating those images, I'll go a little bit more in detail about this later. By correlating those images, we somehow extract range from those images, and we get a model that looks like this. So this is typically the pure reconstruction approach. So as I said, that's not really what we want to do here. What we want to solve now is a problem where we solve two questions at the same time. We will, on the one hand, extract the same type of geometric information here. So this is essentially an image that encodes, the color tells us how far a pixel is from the camera. So the surface, how far that surface is for every pixel from the camera. And so it encodes close and far, and then some areas have no measurements. Okay? So this is for this image, but then at the same time, we actually also want to look at the images and try to figure out from the image what we are looking at. And so here we've classified in a few simple classes: sky, building, vegetation, ground, and here you see a few pixels that are labeled as our remaining class, which is stuff, which is all the rest. And so, or clutter. And so what we try to do now is combine this information, which I actually extracted separately, combine that information into extracting a joint, in solving jointly the reconstruction and the segmentation problem. The reconstruction and the segmentation, which actually is also the recognition. So we try to separate the reconstruction, the geometry there, in separate parts, a part that corresponds to a building, part that corresponds to vegetation, part that corresponds to ground, etc. And what's interesting to notice, and we'll get more in detail there a bit later, but what you can immediately notice, not only is this a richer representation, it has semantics, we actually know that this is building and that this is ground, but actually if you look qualitatively, there's a huge difference in the quality of the reconstruction. So just the geometry is actually hugely improved here compared to there qualitatively. You see in particular we have all the ground reconstructed, we have most of the roof structure in place, where this was actually missing in the pure geometric reconstruction. So we essentially, by doing both problems together, we're actually able to get much better results. And so I'll explain that later, how we get to that. Before we get there, let me show you a few things, a few other projects that go on in my group. There should be sound here, but I'm not sure if it's, I guess there's no sound. So I'll unplug it. I don't know if it's loud enough.
3D scanning aims to capture the geometry of the 3D.
Do you hear it? No, okay, so then I'll...
Existing solutions require a complicated setup, are often hard to use, and might not always work outdoors. The idea...
Okay, whatever. So I'll just explain you then.
The supplementary sound is turned off. This is when you try to...
Oops, that's the wrong button. Okay, I'll just explain you myself then, no problem. Okay, so this is a recent project that we've done in my group. It turns out that actually these devices. Okay, so it turns out that these devices here, that mobile phones are actually fantastic platforms nowadays for doing computer vision or other image-related applications. So in this case, we ported a whole 3D, a whole image to 3D pipeline on a mobile phone. There's now enough computational power on the phone to actually, at an interactive rate, as you can see here, at an interactive rate, do a full reconstruction, as you see here. So we first start by tracking the images in real time, and then gradually, as we move around and get additional viewpoints, we recover a full surface reconstruction here. So here it's still ongoing, but you see essentially a surface reconstruction, a dense surface reconstruction obtained from the scene. It also works indoors. It works in many different scenarios. The key thing is to enable this is that we have a lot of computational horsepower nowadays on mobile phones. In this case, we're actually even leveraging beyond the CPU also some of the graphics processor units on the cell phone. This is still a challenge. We're roughly where we were 10 years ago on PCs, but it's actually evolving very quickly. NVIDIA has just announced a new chip that will be fully programmable with CUDA, so will be much easier to put vision algorithms or other algorithms on the phone being executed by the graphics processor. So you see, we first track some features and follow along the camera motion on the one hand, and then after a few frames, we start outputting our geometric reconstruction of the scene. Now, of course, there's many applications of this. Once you start doing this, you can actually print 3D portraits of people, or you can measure buildings. The nice thing is that beyond this being a camera and a computer, it actually also has a number of additional sensors. There's actually gyroscopes and accelerometers in here, and they are very useful both to help us get good results because they tell us the rotations, which is part of what we try to calculate from images, so they help us in achieving that. But they also help us in getting something additional. From just pure images, we don't get an absolute scale of our reconstruction. This is used for special effects. You have a small spaceship and you take images and then you give the impression it's a huge spaceship. But in reverse, for vision, it's a problem. If you have a single camera that moves around, you actually never recuperate the absolute scale of the scene. Now, with the accelerometers that are in there, accelerometers actually do measure an absolute scale, at least a second derivative of it. So you can do double integration from viewpoint to viewpoint, and this actually allows you to recuperate, to observe the absolute scale of the motion that you did. And so you can rescale your whole model this way. So not only can we do the same as we can do offline or with a computer and a camera, we can actually do more often with a cell phone nowadays. Something else, here's a platform that's also capturing a lot of interest recently. It's actually very similar to a cell phone in a sense. It has a camera, it has a computer, and it has gyroscopes and accelerometers for control. But on top of that, it's of course an actuated platform, so it's a little flying helicopter, quadrotor or MAV for micro aerial vehicle. And so what you see here is some of our work that allows these platforms here to fly fully autonomously. So there's no live link, or we don't need a live link. We have a security link to shut it down if needed. But essentially, no live link needed for this to operate autonomously. And so you see here on board, we calculate stereo depth maps, so same kind of color maps here of distances that we recuperate in this case by having two cameras looking forward. And so we can integrate, as we also calculate our motion, we can integrate all this evidence into building up an obstacle map and allow us to navigate the space and explore where there is free space and essentially try to explore the whole space. And so this shares a lot of algorithms with the previous thing. Then another application is on vehicles. So in this case, we do a project together with Roland Siegwart that some of you might still know, and also with Volkswagen and others. And so there's actually a small camera mounted here. There's one over there, and one in the back also in the logo. And currently there's also a stereo algorithm, stereo camera up here, but that will also be integrated in a smaller package. We are currently, our task in that project is to do from these omnidirectional cameras all around the vehicle to map out the environment and allow the vehicle to navigate itself in the environment. So in particular, the difference of this project with a lot of projects like Google's project and so on in autonomous vehicles is that we don't have a laser on top of the vehicle. We don't have a really high-end GPS system to keep you localized at all times. And that doesn't operate inside if you go in the parking garage. This is about valet parking, valet charging actually. So you drop off your electric vehicle, goes park itself, goes recharge itself. You come back at the station, you say, OK, I need my vehicle. It just comes back and picks you up. And then you go, and then you drive yourself. So it only drives in slow traffic, but it can do it fully autonomously without needing heavy infrastructure, just simple sensors. Okay? And so what you see here, we do the mapping on the one hand, and then we also get actually from the motion here, not a stereo rig, but from the motion on the side of the vehicles, we can map out the environment here, the depth around the vehicle to map out parking spaces and other obstacles. This is a map that we get from integrating those measurements here. And this was actually the initial feature map. And I can actually show you a video that's very fresh. This was actually, yesterday I was in Stuttgart. And we had a demo there. Actually, this is only a small part of the demo of the whole route. So notice, there's no one there, right? There's lots of people around it, so we're at the point where we actually can really start trusting the system now. And you will see the vehicle essentially has mapped out this parking spot and will park itself fully autonomously into that spot. OK, so these are the kind of things that you can do by essentially being able to measure geometry, extract geometric information, being both your motion in the environment or the motion of the camera system in the environment, as well as being able to measure obstacles and map those out in the world.
Big spot, huh?
What?
Big spot. It's for handicapped people.
Oh, no, it's not. It's just for women. It's actually a women's spot, if you look carefully. So it's your words. OK. So this essentially, so to get back to the work I present today, so we have, the general problem is we have a number of images of a scene. They can be by a platform that moves and so on. Here is just a collection of pictures of a scene. And then from that, in a number of stages, here's the classical approach in computer vision, would be to first, you extract features in images, you correlate those, you extract them in a way that even under different viewpoints, you can hopefully find the same features back. And then from that information, using robust statistics and robust statistical methods, you can actually recover the relative pose between all of those viewpoints. You build that up. This is called the structure from motion problem. So it's getting the 3D structure from the motion of the camera. And at the same time, you recover the motion. In a second stage, once we know where the cameras are, then we can actually, for pixels, we can, along one ray, we can project in another image, and we can essentially just look along the projected ray, so which makes it easier. We don't have to look in 2D, but just along a 1D scan line. There, we recover the depth by correlating patches in different images. We have a patch here. We correlate, we search along the depth in other images, the projected depth ray, and we get the depth estimate for those points. Okay, so that way we get per view, based on the neighboring views, we get per view evidence of the depth for every pixel or most of the pixels of the surface. But of course, all of those signals will not agree. So we have depths from here, depths from there, from there. Notice, of course, here it's extracted directly from the images. Nowadays, there's also a lot of active techniques. For example, many of you might know the Kinect sensor, which directly measures depth. Actually, it doesn't directly do it. It actually projects a known image into the scene in the infrared domain. That gets observed from a slightly different viewpoint. And very similar to here, same correlation technique is actually used to recover that distance. That's at least for the Kinect, the first Kinect. The second Kinect is actually time of flight and sends light out and bounces back. And there again, you get depth evidence on a per pixel basis of how far the scene is from the camera for every pixel. Essentially, at that point, we get a lot of evidence for the geometry from many different viewpoints. So at that point, the typical approach consists of then computing a surface reconstruction, which is typically formulated one way or the other as energy minimization on a graph. It can be a regular graph, a volumetric grid, where you have evidence. If you're in front of the measured depth, it's supposed to be empty. If you're behind the measured depth, it's at least just behind. It's supposed to be full. And so you put all of this in a volume, and then you can integrate that information. That's actually the technique we pursue here. But you can actually also do this on tetrahedral meshes that are less, that are not regular and that adjust to where the data is. Okay. So this is a classical pipeline. Now, what is really ignored is that if you look at an image like this here, there's actually lots of things that you know if you just look at the image without actually going to geometric information, without correlating multiple images together. A person immediately sees this is a building, vegetation, ground. These have different properties. And so if you can actually exploit that, then you can do much better. And so I'll explain you that in more detail in a second. But essentially what we try to do now is really do things jointly. And so what we'll do is we'll do similarly, we'll try to do a surface reconstruction. Or essentially, in this graph, we'll do a segmentation in pieces of volume. It's a multi-class segmentation, so we formulate our problem. In this case, we have a volumetric grid, regular voxel grid over the space, so it's a three-dimensional grid. And then for every point in that grid, we like it typically to be, we like to have structure, so we like to have neighboring grid cells have the same label. And we like the interfaces. So the separation between a whole blob here that's labeled building, and then a whole blob in front of it that's labeled free space, we like to have that separation be as small as possible in a sense. But in particular here, we like these separations to not only be small, which is the usual technique, but actually also have anisotropic properties. And we'll get to that in a second. Okay, so the applications, as I said, applications are really in for example, driver assistance, city modeling, robot navigation, for example. So currently, we mostly do those things with pure geometry. But actually, you can gain enormously in the flexibility of those platforms and in the tasks that those platforms can perform if you actually also know, if you start understanding the different parts of the scene. Because if you want your robot to not just navigate around, blindly where it can drive or where it can navigate, but actually to know that this is road and this is sidewalk, for example, for the car, or for helicopters or robots that can manipulate things, if they actually know what objects are there, what are objects that are likely to be movable, and what are fixed parts of the environment, then of course the robot can start doing much more useful jobs in the environment. So what has already been done in this space? Well, in terms of bringing recognition and reconstruction together, in the last few years, there's been a number of steps trying to use one to help the other. Okay? So maybe one of the well-known examples for this is the work by Hoyam et al., where at SIGGRAPH, they essentially looked at an image, ran recognition techniques on this, classification techniques, that try to differentiate between three classes. So they try to identify what's ground, what's a vertical surface, and then what's sky. And using just that information, so training a classifier to do that, then they can turn a flat image into a pop-up image. So essentially, they generate the ground surface. They have a vertical surface here for the train, and then the rest is just sky, and so it's cut off, essentially. So that way, they can generate these novel viewpoints. Just by hallucinating it from a single scene, they can get some 3D interpretation of an image. Okay? We also did something in that space where we used recognition, where we would have the image, and from the image, we'd recognize which areas look like potentially planar surfaces or man-made structures, which typically are planar surfaces, and then more organic structures like the bushes and the vegetation here. And so by having this classifier here, you see the output of the classifier, it allows us to improve a reconstruction by saying the parts that should be planar, if this looks like it should be a plane, then we'll force this to be a plane. I mean, by trading off the data and the prior, but we'll tend to try to make it a plane. And parts that might locally be almost planar, but that look like vegetation, we just leave them as they are. So that way we can separate out into fitting planes to the parts that we want to be planes. And in particular, areas that have weak data, like on the windows, which are typically very hard to reconstruct. Here we know, well, it looks like it's a window, or it should be a plane, so we'll just interpolate this as a plane, even if there's missing data. So this is in one direction, taking recognition to help reconstruction. Also the other way around, you can use reconstruction to help with recognition. For example, in this work here, what again Hoyam et al. Did was, from an image like this, they would do an analysis from the vanishing points, so get geometric information out that calculates that the horizon is here, and essentially also have a ground plane reconstructed in this process. And then from that, essentially they would know that they would be able to greatly reduce the false positives in detection of cars and people, because they know that if they get a person flying somewhere up here, this is very unlikely. They know that if there's a person that's this small in front here, it's also unlikely because it's way too small. So essentially, this allows you to put a big filter on the recognition to really help it using the geometry. Okay, and actually also directly gives you a 3D geometric interpretation of all your detections. Okay? In terms of joint work, there's been very little prior to what we did. So probably the only real joint inference, there's been many other works that do one after the other. But where both are estimated together, there's probably only this work here by Ladisky et al., who's actually now a postdoc in my group, but this was done before that. Here, from a number of images, a stereo pair, they would extract at the same time the labeling from these images and the depth. And by doing both together, they could actually get some improvements. It turned out that the improvements were mostly one way. So it turned out that the joint optimization wasn't quite very successful here because it only improved in one direction, meaning that you could first do that one and then improve the other one. Okay? The way they mostly did it was to say that some labels could not exist above a certain height. So it was actually still a quite weak coupling. Okay, so now I'll get a bit more in detail in our techniques. Before going into our new technique, I'll first explain you a little bit of the mathematics behind the standard approach for surface fusion. The way it works is, and actually with almost every computer vision problem, which are often inverse problems, we need to regularize. And actually also beyond that, in many signal processing, image processing problems, you often have some data evidence, and then you also have some priors that say that, well, if I don't quite have all the data, or if I have to trade off data, these will be the assumptions that will help me solve and come up with a meaningful or plausible solution. Okay? So typically, problems are formulated as energy minimization problems. And typically, in many cases, they have two terms. The one term is the data term in this case. And so here we have an indicator variable that tells us on the volume we have this. So this omega is a voxel grid. S stands for each voxel in that voxel grid. And so for each voxel, we have a term that essentially says this is the indicator variable. If it's 1, the voxel is occupied. If it's 0, it's empty. And this term comes from our data, from our evidence. And it comes from it as follows. This is this small triangle is a camera. So this is a camera viewpoint. This is a ray for 1 pixel. So if you have 1 pixel, there's a ray in space that corresponds to it. And essentially, we assume here from the depth that we have a particular distance measured. So we think the surface is here. Given that viewpoint, we think that the depth is this much, so we think the surface is here. So what we put as data term is a negative term behind where the surface is and a positive term in front of it. And it's a constant term. So essentially, if you look at this here, what's the ideal solution? It looks like this. The optimal solution for XS is as follows. As we try to minimize this energy, we'll have zeros everywhere here because there's a positive cost here. So we'll have 0 everywhere here. And then here, as we start getting a negative cost, then of course we want to turn this to 1 to get here to get full account of the negative cost here because it reduces our energy. Okay, so we put this to 1, and then of course this should be ideally a binary variable, 0 or 1. We'll actually solve all of this as a convex relaxation. So these are continuous variables, but in most cases, in particular in the binary case, it will actually always or be blocked at 1 or blocked at 0 after the optimization. Okay? So that's a simple case when there's no other term. Of course, we also have this other term, which actually says that you would like to have the gradient here integrated over the whole surface that you reconstruct. So essentially, the gradient is this place here where you transition from 0 to 1. So in a binary case, it's just it's a 1 here and 0 everywhere else. So you want to minimize the number of transitions, essentially. That's what you minimize here. Now, there's this function around it that essentially looks as follows. So this is actually a gradient. So it's a vector. It's a 3-dimensional voxel space. So there's actually a gradient in every direction. So it's a vector. And so if you look at it here, it's a spherical. The penalization we do, it's not just counting its edge, but it's actually a spherical penalization, which means an isotropic penalization of the surface area. Okay? Now, of course, it's a voxel grid, so it's discrete in this. The representation is discrete. We approximate it here by having actually this. In practice, we'll have at the interface, typically we'll have, as in images, mixed pixels. We'll have mixed voxels. And they will actually allow us to have non-integer values here for the normals or for the vector, which represent the normal of the surface. And so we can actually meaningfully enforce this spherical prior. And of course, in this situation where you reconstruct all the surfaces at once, which means you reconstruct ground as well as building, as well as trees, all with the same prior, because you don't differentiate between them, the best thing you can do is have something isotropic. Therefore, you have to go with isotropic. Okay? However, if we start mixing in the information from the recognition, then we can do something better. So first, what do we do for recognition? Well, in this case, we use a standard classifier solution. So from an image like this here, what you see here is the most likely label. But what we actually use is actually the probability, so the negative log likelihoods here, represented to, so when it's more, so here we have the different intensities represent different likelihoods of different classes. So this is for each of the labels here. So blue is very likely here, so this is likely to be sky. This is likely to be vegetation here, etc. Okay? So we don't have a binary decision. We actually leave the decision for later. Right? We don't want to make early decisions. We try to do all the decisions in one big optimization, no early decisions. Right? Because you always lose information if you do early decisions. And actually, here's a few more examples of how this looks like typically. Again, if you discretize a solution, but this is what we work with in the optimization. Okay, so how do we work with that? How do we extend our initial approach here to actually take this information into account? Well, first, in terms of representation, instead of having a single voxel grid, we actually instantiate one voxel grid per class. So this will be expensive. Instead of one volume, we now have, in this case, 5 volumes. Okay? And it gets worse, I'll tell you later. So we have 5 different volumes now, and for each of them, we'll actually set up the same, we have the same data term here, initially for the depth information. But now we actually also have information about which class it is. So essentially what this says is, assuming, and this is simplification, assuming this is a correct surface estimate, then if our surface is estimated to be here, and this actually represents the uncertainty, then we assume that behind that uncertainty, we're definitely inside the volume. Okay, so this implies we assume a minimal thickness of the volumes we observe. But essentially here we put a value here, a penalizer. This is a positive value, so it will be a penalizer for the different classes. Okay, so we give them the same geometric information, but we add, inside the volume, we add some information that says, I think this is not a building, so big penalizer. And I think this is probably vegetation, so a small penalizer. Okay, so directly we take the information we have from our classifier and put it also in the volume. So we have the geometric information and the classifier information. So again, if you have just this evidence here, this would be the optimal solution, right? It says this is a bigger penalty than here. So of course, what I didn't tell you is the sum of those two, the sum of all the volumes needs to be 1. We have 2 zeros here. There's actually a third one that is free space, and that one is 1 here, and then goes to 0 once we transition to vegetation. And of course, vegetation, if you compare those two solutions here, of course, vegetation will win out because it has a smaller extra cost here than this one. Okay, so that's how. And so essentially what we do is we throw all that evidence into the scene, into the volume, or into the multiple volumes. Also to give you an understanding of what we're doing, in practice, as we start putting multiple measurements in the same volume, they will overlap if we have redundant measurements. And then in the end, we might have to put the surface not here, but here as a best trade-off. So what is the penalty that we generate by moving the solution from here to here, that our final surface lands here? Then essentially it's the integral here. That's the penalty. Okay, so what does that correspond to? Well, clearly as we move this further away or closer, it's linear. So this is just an L1 or total variation cost term, right? So it will vary with the distance, linearly with the distance. So it's a robust measure of integration. It trades off all of our measurements in a robust way. Okay? And then, of course, one thing I didn't tell you is if we observe sky, then that actually is evidence that the whole volume is empty along the whole ray. So that's a special case. Then the second part, which initially was an isotropic regularization, in this case, we actually, once we start dividing things in multiple classes, then we can do better. Because if you look at, for example, the ground class and the building class, they have very different properties in terms of what normals you are likely to observe. Right? So we had this fully isotropic penalization of surfaces. Here, a building is likely to have very nice vertical surfaces, many of them. Right? So we want to make that cheap, because if it's a building, the surface is not likely to be like this. It's likely to be like this. For ground, the surface is likely to be horizontal or close to horizontal. It could go up. This is actually a city model from Zurich. That's where we trained some of our data from. So it has some hills. But obviously, you don't see ground upside down, for example. So we can heavily penalize ground going upside down. Okay? So how do we do that? Well, we actually use the concept of wolf shapes. These are convex shapes. This is actually a concept that comes from crystallography. So if you have a certain energy field, which is here represented, so that you have to imagine it as a 3D shape, but it's here represented as a slice, a 2D slice of it. The black curve here, so this is essentially for normals, right? So you imagine all possible normals. And here, we tell you how much we penalize a normal. So you see there's this black curve here, which says that essentially in this direction, there's no penalization. In this direction, there's some penalization. Here, there's maximal penalization for this particular shape. So the black shape is how much penalization we have. This actually corresponds in crystallography to the energy field of the atoms. And then the red line here, that corresponds to the convex shape. That would correspond to the crystal shape. If you would build crystals with something with this energy function, it just gives you a single line in this case, so a vertical line. So this would be a shape that maximally prefers horizontal normals, essentially vertical walls, right? Zero cost for horizontal normals, so for vertical surfaces, and then a bigger and bigger cost as you deviate. So this is one shape that we have a small vocabulary of shapes here. Those are also very efficient to compute later in our optimization, to use in our optimization later. So we have this one, which is tuned to be good for walls. And then we have another one that we chose to be a good representative for ground surfaces. And so this one is essentially a big penalization anywhere looking down, and then a smaller and smaller penalization as we get closer to vertical, with still some amount of penalization here. Okay? Now, there's still parameters here. We have to choose how big we make this penalization for vertical. And here, we actually also have to choose how long this stick is. Okay, so how anisotropic this is and how strongly we penalize one versus the other. Okay, and on top of that, of course, just this type of transitions, which would be, for example, a transition from building to free space, this type of transition itself has some likelihood. So that actually will be used. We incorporate this by doing a Minkowski sum of this shape with an isotropic probability. So we end up with something like this here. Okay? This is actually not per class, but it's for transitions between classes. Surfaces in our model are transitions from one class to another. Okay? So essentially, if we look here, we have building transitioning to ground, or actually we may do building to ground this way. Here, we'll end up with, of the different possibilities, selecting this one. So we have this shape, and the isotropic shapes, right? So those are our three choices, and we let the algorithm figure out what makes most sense. And actually, if I forgot to show that, but it's actually learned from this model here, okay? From this city model, which was obtained through standard photogrammetric techniques, not by us. This is we asked it from the city of Zurich, so we got this model. And so we can learn what, of this vocabulary, which of the shapes here, which of the different shapes is the best for modeling a particular transition, and what parameters we should choose that best work for the observed surfaces in the model. Okay? And so you can see we can now express in particular how building and ground interact with each other and with other classes. Of course, for vegetation, we didn't have really data of statistics of vegetation, and stuff also not. Those are actually classes that you can assume to be isotropic. And so at this point, we don't do anything smarter than assuming they're isotropic. And so we just penalize them like this. And so whenever they interact with stuff or with air, et cetera, and also depending on how likely they are, so if we make them small, they're less penalizing. And if we make them big, they're more penalizing. So actually, those should be bigger because the one from stuff, we want to have a minimum amount of stuff to explain. So we want actually this to be bigger. Okay, so how do we eventually put it all back together? Well, if you remember in the previous equation, this looks very similar. Same data term here, except that we now sum over all classes. So I is to the class index, right? And so and also I don't have them written down here, but there's a number of additional constraints that enforce consistency. In particular, they say that the sum of all the xi's at a particular site S has to be 1. And exactly 1. It has to be 1 because free space is also a class, right? So it's or free space or one of the other classes. So it's always, the sum is always 1 here. Ideally, it's an exact 1 and not a mix of different variables. So this is essentially with the previous terms here that we had, the unary terms. And then we have a surface, an interface penalization term. Here we have 1 per class transition, okay? We have to express free space going to building, free space going to ground, et cetera, et cetera. So we have all the pairs. So we actually have 10 of those different transitions. Given 5 classes, We have 4 times plus 3 plus 2 plus 1. So we have actually 10 different classes. And for each of those, this is a gradient essentially, a generalized version of the gradient here. We have that for each transition. So essentially, this is 3 numbers, right? It's a 3-dimensional space, so it's 3 numbers for the to express the gradient times 10, because we have 10 possible class transitions at every point in the volume, essentially. Okay, so this is very expensive. This is 5 floats per voxel as we have convex relaxation of our problem. And this, of course, also, we need to have these, be able to express complete normals. So this is essentially 3 times 10, so it's 30 numbers. So we have 35 numbers per voxel to express this. So it becomes very expensive, but you will see it's quite powerful. And then, of course, we have a few additional ones to enforce the constraints, so dual variables that allow us to express the constraints, that the sum should be 1, the fact that there's full consistency between the gradient and the volume itself. Of course, these are just the gradients of this volume, so there's full consistency. So those are all expressed through the consistency between those things are all expressed through these additional constraints, dual constraints. Okay. And then it's optimized using a primal dual algorithm mentioned here. So here again, putting all this back together, we have this behavior in the volume that we put in the volume as data terms. And then we have here the different class behaviors or class transition behaviors, where we minimize here this over each surface. We will minimize this. And so I can now show you some examples of how this works. So here's one example. I'll replay the video here in a second. So this is a square in Catania in Sicily. So it's the market square. And so what can you see here? This is the standard approach, and this is this approach. It's using exactly the same geometric terms. Okay? Purely the same geometric terms. The only difference is here class-specific regularization. Or class transition-specific regularization, where here we just do the standard thing. Okay, so what do you see as a difference? Well, the main thing is the whole ground is missing. Okay? Now, why is that? Well, this is the starting point of our optimization for this solution here. And so essentially, where you start with the optimization, here we just show you the most likely label. And then make surface out of that. But so it shows you the most likely label, meaning that almost everywhere empty is still the most likely, except at a few places where we have very strong evidence of building. Our classifier was in full agreement. It said building, so these, as we actually see the building surfaces frontally, we get very strong evidence for them. So they come out right away. Okay? But the ground surface, which is observed very obliquely, and if you correlate, because of the change of viewpoint, you actually get pretty poor correlation typically. So you only have very weak evidence there, mostly in the center where a lot of images are overlapping. Okay? So we have a little bit of evidence here. Now, what's the cheapest way to explain that evidence? If you do it isotropically, you see it here. It has a little patch that it really has to explain. Well, the easiest way to explain it is to wrap it around, package it up, and give it. That's a very small cost. Okay? That's what's happening here. But in this case, we don't have very strong evidence, but we know it's ground. Okay? So if we say this is ground, explain me ground in the most likely way, start explaining, no, that's very expensive to turn it around. Okay, I cannot turn it around. I cannot wrap it up. So essentially, you start diffusing it out, because the only meaningful way to explain that ground is to look for other ground support somewhere around. And so it will gradually diffuse out, fill up the whole ground surface. And then you will see something very interesting. You should look towards the end of the essentially it's a diffusion process. So towards the end of the diffusion process, you will see over here where there's a building. You see the building has little full evidence, and you will see what happens around this region here. Okay, so let me play it again. Okay, so see, gradually the ground is diffusing out. So now you see what happens, right? So the ground diffuses out as horizontal. This is the most likely thing. And then the building that didn't quite know where to end because it didn't have evidence, it was floating around a bit back and forth. But then as soon as there's actually ground under it, then it's very clear what the right solution is. A building connecting to the ground is very cheap. Okay, and so you can, instead of having a surface dangling around here and a ground surface, the building to ground is as cheap as ground to something, to free space. So essentially, suddenly, you can collapse two surfaces into one, and that becomes the obvious cheaper option. Okay? So it takes a while because it's voxel by voxel diffusion in a sense, but eventually you come up with a meaningful explanation of the world. Something that a person would have to complete, data would complete it also in this way. So with very little at the level of a voxel saying how voxels interact with each other, we get global behavior. Of course, the same as crystallography, it's the same thing essentially, right? So this is quite interesting. Here's also, so of course this was all a relaxation, it's a convex relaxation, so this whole problem always go to the same solution in this case. And so the question is, does it go to a useful solution? Because it's a convex relaxation, it could end up with essentially all of the values being some mix of all 5 classes almost equally represented or so. And then it's not very interesting. But if we look at this, it seems that this relaxation actually quite strong relaxation. And although there's no guarantees, no theoretical guarantees, here's a slice for our volume, somewhere halfway here. And what you see is that, of course, here behind the bushes here, it's kind of unclear. You see there's a mix of free space and bushes because it doesn't quite know what to do. Here also it's a bit fuzzy behind where you didn't observe the surface. But for the rest, it's actually very binary. So there's almost no mixed colors here. So it's quite strong binary solution almost everywhere. We actually also have some explanations of why this is probably the case. In particular, there's a much cheaper relaxation that doesn't model every possible interface, but that models one versus the others. If you do that and you interact with 2 classes in a corner, you confuse a corner here. In this case, it's a corner if you model this interface and that interface separately. But if you model as red versus the rest, then this looks as an interface this way. And so that's why this less tight relaxation, which is this one, this is linear in number of classes. That's why this actually doesn't quite do the full behavior you want and will tend to round off your solutions, or in a completion experiment here, you see it kind of rounds off and gets mixed results in a big area, while this one actually gets much tighter things. Of course, there's still discretization and so on, and it's not perfect, but it's much tighter. So here's a few more visual examples. Let me actually skip this in the interest of time. Just show you a few more examples here, where here you see typically the ground gets completed, but notice the ground gets completed, but it's not a strong prior. It will not like flatten everything. You see here, there's actually evidence for stairs and so on the ground. It will follow that. So it's a trade-off, but it doesn't overrule and somehow make just little square boxes out of everything. So typically come out with quite nice results. OK, so maybe beyond that, can we, just from looking at the image, a person can actually get a lot of information about 3D of this scene. We know that this is closer and this is further, right? We can actually already guess a lot of the depths in this scene from a single image. So we tried to do the same. I won't explain this in detail, but just give you an idea. So what we did was, for images, solve, and this is actually with Lubo Ladisky now in my group. So we try to jointly do the classification and the depth estimation. And it turns out that in classification we do better. This was just classification. This is doing both classification in the class, but also at what depth range. And we actually do better on purely the class, on which class we get. The way we do it, what we actually assume is that most of the effect, if you look at cars at different distances, most of the effect comes from the difference in scale of things at different distances. There's a small residual effect of perspective, but the biggest difference, if I see people in the back of the room and I see faces in the front of the room, the biggest difference is just the size of the image. Okay? So essentially, in the first order, you can compensate that by building up a pyramid and doing a classifier in the whole pyramid, and essentially do classification on having an object at a particular canonical depth or not. So instead of just classifying, is the car or not a car, we say, is it the car at this particular distance? Okay? And then we have positives of all cars at the same distance. Here, you see they're all at the same scale roughly here. And other objects or cars, like this here, at different distances. And it turns out that there's really signal there. So from a single image, you actually really get a depth signal. So here you see essentially this for each of the classes, what depth versus this logarithmic scale. So this is the right depth. This is the positive training range we used, and this is the negative training range. And you actually see that within here we have a very strong signal, and outside of the negatives are classified as negative. Okay, it turns out something else we can do. I won't explain you this, but we can actually, from a single image, also as a separate problem, get most of the normals. This is ground truth, but with Kinect, they're actually very noisy normals. These are actually the normals that we get out. And you can see qualitatively, it's almost perfect. We're actually very surprised, and we looked for a long time to see if we hadn't somehow used the training data as test data and things like that. But it actually works really, really well. So it's actually here. This is the prior art by another group. And this is our technique. And so you can see qualitatively this everywhere it really makes sense. There are some mistakes here and there, but it turns out finding normals from a single image is actually, it seems, not a very difficult problem. We were surprised. Here's the same on actually an outdoor data set. So the Kitty data set where also we get, you can see quite nice normals actually of cars, quite consistently extracted just from this single image, getting all the normals extracted. Okay. I will actually, I think in the interest of time, I will skip this mostly, but essentially the idea we had was to extend now from having something that could happen anywhere in the volume to try to go to objects where we have a car here and we detect a car. So there is now here first a detection. But then once we detected the car, we have a similar optimization as before. But in this case, we actually also make this term dependent on where we are in the volume. So what we're saying is, if we're up here in the volume, our normal for a car is very likely to be a normal pointing up. But if we're here, we're very likely to have a normal pointing out this way, and here that way, and then around the wheels, etc. We can essentially say where in the volume we expect to see what normal. So we train that from downloading a few models from the web. And then we express our wolf shapes. Instead of having a predetermined vocabulary of 2-3 different wolf shapes, we actually have a full tessellation of the sphere. And we have to guarantee that those remain convex for the whole problem to remain convex. But as we do the intersection of half spheres, it's guaranteed to always be convex. And we just move those closer and further away from the center to penalize more or less a certain normal. And the only issue with it, so it directly maps actually here these distances from those half planes, directly maps to the probabilities. The only problem is that it might ignore if in one direction is very likely and the next direction is very unlikely. We cannot express that. Because the convex approximation of it will essentially mean this is very likely, so we move it very close so that there's small penalization. And of course, the half plane will cut away anything that we put far away. So we can underestimate unlikely things, underpenalize unlikely things, but the likely things are always properly accounted for, which is fine. It's kind of the best you can do for regularization. So just to show you the results here, this for cars. Something interesting by working this way was that although we don't really observe the surface under the car, and initially it collapsed with the ground, we actually realized we could also learn that and learn the point where we transition. So we can actually learn in the volume because we can model separately different class transitions. We can say a transition from car to ground only happens at the wheels. And we train this from our training data. So we know, without seeing it in this particular example from the data, our regularizer had this all built in. And so it can actually instantiate the contact points and make sure that this stays away from the ground. The car doesn't collapse with the ground and doesn't fuse the two surfaces into one. Okay? So here, same example with bottles, which are specular, very difficult to reconstruct from images. And so you can see that we get actually very nice reconstructions of those particular examples up there, while the naive reconstruction approach doesn't quite achieve that. Okay? And so that's essentially what I would say. This is actually in the formulation of Jitendra Malik. Nowadays, he's going everywhere and talking about doing reconstruction, recognition, and segmentation, which he calls reorganization, to have 3 R's. Essentially, this is what we're doing here. We solved the 3 problems at once. So we decided what each surface was, which is the recognition problem, where it was, in a sense. So essentially those surfaces, the geometry of the surface. But in our case, it's at the same time in the images. If you project this in the images, it's at the same time the actual segmentation in the images of the different classes. Because just projecting this in the original viewpoints gives us the full segmentation also of the image. So we really solved in one clean optimization with a convex relaxation we solve all three major problems of computer vision all in one nice formulation, taking the raw evidence from measurements, depth, and from classifiers that tell us what they think they see. We can combine those and then solve one problem and come up with qualitatively much more meaningful results. Actually, something that I cannot show here, I don't have the illustration material, but you can actually take away the tree here. You will actually have a proper wall surface that has the right priors behind it, that is a flat wall behind it. This is automatic here, right? Which, of course, here is just unthinkable. You cannot even start thinking how you could do that here. Okay, so that's what I had for today.
Thank you very much, Mark. So, questions, comments? I'm sure they are. So please, who wants to start? Who wants to start? Please. Yeah.
So how fast can the algorithm perform? Can you do real-time?
No, it's very slow. So we haven't tried it on GPU. This is actually, because it's all local operations, it's trivially parallelizable, all of it. But as you've seen, it's very expensive because we have per voxel about 35 for 5 class, 35 or more because of the dual variables. So we have a lot of numbers to manipulate. It needs, as you can see, currently we have a voxel grid of a few hundred wide. And as you've seen, some of the behavior is very long range. So we need hundreds of iterations to propagate the information. So essentially, we need hundreds of iterations over huge amounts of data. So it is quite slow currently. It takes hours for these type of results. But because it's fully parallelizable, there is actually hope to make this much faster. We haven't, it is not on GPU yet, mostly because we didn't have enough memory on GPUs to do something useful. But of course, there are probably ways to tie the problems up and do this. Here, it's just the clean version, and so it takes very long. But there are many optimizations thinkable. If you know from the initial data that some part is definitely free space, or maybe there's only 2 classes in play, then you can do a graph cut or other techniques that could be much faster locally in that part of the volume. There are many ways that you could accelerate these things, but currently it's very slow. If you do the clean, naive optimization of this whole thing, it's a very expensive process.
That was also one of my questions, since there is an electrical engineering community here, whether there is an architecture which would be more adequate for that kind of problem in terms of hardware architecture.
Well, so definitely GPUs are much more appropriate for this. And not this particular thing, but the same type of optimizations. In my group, I've been put on GPUs and perform very, very fast. So that's definitely good. So essentially anything that, you only need to talk to local data and you iterate many, many times over that same local data. So it parallelizes very, very nicely. So any architecture that would support that, it's ideally at some type of 3D arrangement that, for the data, it's a 3D volume here. But, beyond that, it doesn't need much. Of course, some floating points are.
Yes.
So you're starting with some evidence, some well-known geometry. So again, there are obviously some difference in the quality of the geometry between the parts and the So how do you extract the quality of the geometry?
So I'm not completely sure I understood completely, but so this is more or less what you would get with a simple regularizer. And so one important thing to notice is that so some places are very close in both. So this is actually where essentially this model is very close to the initial evidence. And then there's other parts that are really fully coming from the prior. And so it would actually be interesting to characterize that, because if you want to use this reconstruction, you might want to know if you drive a rover, some vehicle over here. You might want to know if you really measured it, or if it's just hallucination from your interpolation, essentially. Right? So it's a smart interpolation, but it's still interpolation, or diffusion. So essentially, this would be an interesting question to be able to say, could there have been another solution, that would be different from this, that is almost the same energy? Right? So around here, not. This is the solution, and you cannot move it away from there. Here, you could probably, if there would be a bit of evidence saying that this point of the ground would be lifted up by the ether, I could find another solution that's almost as cheap to do that. Right? So essentially, that would be interesting to characterize. That would probably be even more expensive to do that, but it would be very interesting. So in the end, we hope to have everything binary to essentially say that here in this voxel in the volume, it's purely air. So at the end, we hope to make a decision. So we hope to say this is air. In there it's ground. Behind there it's it's wall. Behind it water, and so on. So we hope that we have at the end that the solution says uniquely, I really think this is ground. But it will most cases it will converge to something, even though that if you would do the full joint distribution, it would be not binary at all. So we don't do a joint distribution. In the end, we hope to get with one inference most likely solution with minimal energy. There could be many other solutions with a very similar low energy. That we don't really know anything.
How do you deal with the situation when you have, for example, for vegetation, a leaf on image and a leaf off image? The same also you would have a...
You would have what? I didn't hear.
A photograph with leaves. Photograph with leaves.
Oh, yeah. Well, I mean, obviously, you'd need to expand your model to, so you could model that in your, So this is essentially a model that assumes a certain, that it's the same, the same point. So the geometry there would have changed. And so you could model that probably. I mean, it would be very interesting to model that and to, for example, say like, that one evidence needs to be contained within the other, for example. So you can have the tree would be a smaller volume in the winter than in the summer, for example. And so you could also have the classifier in the winter be different for extracting the image evidence initially than the summer classifier, for example. So you would have to model that somehow to handle that properly. You'd have to model that in your model to properly handle it. Otherwise, you could have funny results.
More questions, yes, please.
So, if you don't get a single label for voxel, I'm just curious. So, for example, you get two labels, each of them, like labels, each of them is 0.5 chance. Is it that it's really one of these two, or is a third one? Did you do this?
Well, I don't think we really have a theoretical answer to this at this point, but I think so it certainly doesn't have to be, because now we could have a single class, and it could still be another class, right? I don't think you could ever draw that conclusion, because even with a single label, you could have a fully binary labeled solution in the end, and then that's just the most likely full configuration at the end, but you could still have a completely switch of labels. That could be almost as good explanation. And given a bit of extra evidence, you could flip everything off. That's actually why it's so expensive currently, is because we initially make no commitment. We really allow for having every voxel take on every label and consider everything. And so this can take, this means a little bit of extra evidence could somehow flip the whole solution over potentially. But so it's not because you end up with a binary solution that it's a clear unique solution. That's certainly not the case. And if there are only two labels, there could be a third label that would come in from somewhere else that would diffuse out under a slightly different, that would win out somehow given a slightly different measurement, something like that. And so this would be only slightly less likely, for example.
Great, well, thanks. So since you cannot come with proofs of optimal solutions on the flip side of this is economics under examples, I think work very badly. So in the single image case, you could put visual illusions as the data and see what the algorithm comes up with.
Yes, so here so it depends, of course. So I don't think we have at this point an intuition of what would be the equivalent of a visual illusion here, because you know, so obviously we have relatively strong priors here on what we assume. And so as long as things follow those priors, it seems to, so we haven't found a discrepancy where something follows the prior, but we don't get the right solution. So I think, you know, with the visual illusions, it's because people get fooled, and you know, there's a lot of us looking at the world all the time, and so there's people, you know, figuring out that there are visual illusions, and then often they can be transferred to some, you know, algorithms can actually be used to validate some hypotheses of the human visual system, and so in this case, we're not doing this, you know, it's not clear, so we don't have the same kind of, you know, way to kind of get by those discrepancies between the prior and then what comes out of the inference. And so I don't have any examples where I found out something funny happened. I've seen things that I showed you with this completion, things that, you know, you see like, hey, this really makes sense. We haven't had the opposite yet on data. Of course, what we do see is actually sometimes holes that get filled that shouldn't get filled. So there's, maybe I can show that very quickly. There's, okay, so here, no, I don't see it here, but actually on this side of the facade, there's actually some holes that in the proper, that in this model, you get the proper arcade, and our model, you know, makes an arcade more expensive. And so, essentially in our model, this just gets, you know, filled up. So this type of things happens.
Last question?
Instead of using the wolf shapes or wolf function, would it be possible to build a kind of dictionary for city model that you are doing? I don't know, sparse dictionary or something?
Those wolf shapes are essentially any convex shape. I mean, we call it a wolf shape. It has to be convex, and then it's, but we can, yes, exactly. We're now working on actually, you know, as we've now gone to learn generic shapes at the local level here, directly penalizing normals. Now, of course, you know, if your prototypical model, this is something we're working on. The prototypical model is like a house. You know, you can actually take the house as long as it's convex. You know, you can just say my house is a wolf shape, and then you will by default get house-shaped things as the cheapest thing. Yes, this is exactly what we're doing, and we're looking at extending that to non-convex shapes and so on by having multiple classes of the.
So if you have more questions, now we'll have the reception. So you're all invited to take a drink and some, I don't know what, something to eat. Just next to here.